this effect where if you sample graphs at the MPLE in this case, then you get this approximated likelihood on the right, the true likelihood is the left, approximated right. And in the approximated, you see that the contours are so far gone from the true MLE that if you were then to go and sample graphs at wherever the approximated MLE is here, it would be hopeless. It would never get to the true MLE. It would never converge. So you have this problem when there happens to be a large distance between where you sample graphs and the true MLE. Okay. Now here's where our method comes in. Well, the idea is that rather than sampling graphs at one point, we would use our merged normalizing constant estimator to sample graphs at multiple points in the parameter space and hopefully improve that estimate. How do we get those multiple points? A heuristic, which I'm about to describe. Suppose we start with this 20-node graph here, which we want to estimate the parameter on. And then the idea I basically have is to take a small subset of this graph and estimate the MLE on that small subset. And that can be done relatively quickly because it's a small subset. In this case, I'm going to describe quickly how we get that subset. Suppose we're looking for a subset of the graph of size 10 nodes. Okay. Start by picking a random node, and then we begin to snowball. Snowball. Take all their friends. Take all that node's friends. Okay. And now we actually have hit 10 nodes. So we stop right here. Now if you don't happen to hit exactly 10 nodes, there is some corner case logic. But just this is how you get the graph. And then that blue graph there is the one where we would then go and estimate the MLE on. And if we do this many, many times, each time estimating the MLE on one of these subgraphs, we get that scatter on the left for this particular example. So what you see is that the true MLE is there in green, the pseudo-likelihood estimator is in red, and then all those blue points are the MLEs of the subgraphs. That's the heuristic we use to get these starting points. And notice that they have a lot of scatter. Well, that's a good thing, because what we like is a range of these parameters around the true MLE, which we have. Now, granted, we have some that are not that useful, but we have many that are pretty useful because they're pretty close to the true MLE. So now suppose we actually go and use these. And let's just say more generally that we use S starting points, and S minus one of them are these SMLEs, and one of them we use the actual pseudo-likelihood estimator. Now, consider these two scenarios. Number one is where you use only one starting point. Then you get the approximated likelihood in the middle. That's the one that we just saw. It's the one that causes problems. Okay. Now suppose that you add to the mix the pseudo-likelihood estimator in blue, and the two things in green that are a little hard to see, but those are the subsample maximum likelihood estimators. And suppose we sample graphs at each of those points. So now we have three sets of sample graphs, one at each point. We can form that into a unified likelihood approximation using the machinery I described originally. And if we then go and approximate the likelihood and find the MLE, look, in this case we prevented the non-convergence, and now we've gotten a set of likelihood contours, this one on the right here, where the approximated MLE, the thing in orange, is very close to the red dot. So that's a good thing. So by using this machinery, we've managed to get the algorithm to converge in a place where, using the standard techniques, it would not. Okay, here are the results on a large number of graphs. I've highlighted in red here. In Geyer-Thompson is the traditional method on the left. That's of my 25,000 some graphs, there were around 1,000 of them for which the algorithm didn't converge. But now suppose I did what I just described and use multiple starting points. Then what we have is far fewer non-convergences. 877 if we use one additional starting point, and 557 if we use three. Okay. So we managed to cut down on these non-convergences.
Have you
Yes?
taken a look at what those graphs
Contingency table?
are like?
Yes.
No.
Oh, okay.
What those graphs are like when you don't converge, when you didn't converge.
Yes, that's right.
So did you try other things which could make it converge?
No, I mean, I haven't done too much detective work in that area. I mean, what it tends to be is it's hard for graphs that have a large number that are dense with edges. They tend to be harder to converge. And I think that has something to do with there being a lot of graphs that are like that, right, relative to graphs that have smaller numbers of edges, but I'm not totally sure yet. Okay. All right, so now, I mean, suppose we do all this. Now remember the original problem. The original problem was that we have these sets of these graphs, and we've observed numbers of edges, triangles, and stars. And what we wanted to do to help us identify which ones were similar with one another was to estimate these parameters.
These are real graphs, or these are
Yeah.
from real data or from data you generated?
Right, real data, yes. These are the prisoners, the students, and the assembly lines from originally. Okay. Now, then we go and estimate these parameters. Okay. Now, first of all of them, in this case, converged under our method, which was good. But the two ones in red, the ones there, and this kind of gets to your question a little bit, those were the ones for which they didn't converge under normal Geiger-Thompson. You see these ones here that tend to have a lot of stars going on, a little harder to make them converge. But if you notice, if you look at the parameter values, the orange parameter values are all pretty similar with one another. The greens are pretty similar, and the purples are pretty similar each. So by knowing these parameters, it helps you identify the generative process that produced the graph. And that would help us group these graphs if we were to estimate by estimating these parameters. Okay. Conclusions on this. Well, first of all, there are two main points that kind of recur through my dissertation here. Number one is that we've managed to reuse expensive computations, this recycling principle. And we also use some heuristics, in that Monte Carlo methods can often be an art and not a science. In this case, the heuristics we used were to build this mixture distribution P gamma. It was a mixture of different points. That was a heuristic. It was an idea, and it turned out to help things. And number two was that we used these SMLEs, these subsample MLEs from snowball subsampling. Again, a heuristic. There's no theoretical guarantee that these SMLEs are near the MLE, but they help in practice. And we ended up using them to improve the algorithm. So both of those were heuristics.
But it's not entirely heuristic that if we use more starting points, then we're going to do better.
Yes, well that's correct. That's more like the recycling principle. That if you reuse computation, you tend to do better than if you waste it.
Because just the original snowball sampling doesn't dominate pseudo likelihood or vice versa. Neither dominates the other, but we can incorporate all of those as well as other heuristics, and sort of like combining heuristics is a non-heuristic way to do better than any one heuristic.
Yeah, that's true. So it's like an ensemble model for graphs here.
Yeah.
Yeah. Okay. Makes sense. Yes.
You didn't have standard errors on the previous slide,
Yeah. Right.
but do your methods extend to getting Fisher information?
Yes, they do. I didn't put those. And the people would probably be falling asleep more than they did if I put those formulae here, but I do have them in the paper. Yeah, and they're there. You can easily get it from the approximated likelihood. Think about taking that approximated likelihood, and you can get its. There are analytical formulae for its first and second derivatives, which can then be used to get those standard errors. Okay. Any more questions? All right. Okay. So now I'm going to dive in. We're at about the 45-minute mark here, so I'm going to take a little breather here, and I'm going to dive into the next part of this, which is protein folding. Okay. So get ready, put on your seatbelt, and now there's going to be a fun intro again, so you can wake up for a minute. All right, so protein folding, the basic problem is this. Suppose we start with this sequence of amino acids. They're represented by letters from A to Z. Each of those represents an amino acid, which is one molecule within this larger protein. And there's a number of them that make up the protein. Now, suppose you know that the sequence of amino acids that make up this protein, in other words, the type of molecules that are inside it, but you don't know their positions in space. The goal in protein folding is to predict those positions. And in this case, that sequence I just gave you looks like this in three-dimensional space. It's a happy structure here. I'm sure. And the reason you want to predict something like this, by the way, is there are people out there, and I'm not one of them, who could do things with this prediction, do useful things. And I can't tell you what all those useful things are, but they involve cool and fun disease curing, and et cetera, et cetera. So being able to predict the structure is where my expertise ends. Okay. So how do you do it? Well, there are two steps. Number one is you have this energy function which describes how good a candidate structure is. Suppose you were to arrange them in some random structure. Well, it might not look that good relative to the energy. There might not be favorable interactions among the atoms. The energy usually depends on these pairwise interactions between atoms in the protein. And if you don't come up with a very good structure, then the energy will be high. The better the structure, the lower the energy will be. Now that energy function is often learned from data itself, which is kind of an interesting problem, not what we'll discuss today, but what we will discuss is once we have that energy, we have to minimize over the space of all possible atomic configurations. So consider each structure, then evaluate its energy. What we'd like is to find a structure that minimizes the energy. We do that usually by starting with an initial configuration and tweaking it gradually one step at a time to lower the energy. Now, I'm going to give you an idea of the scope of this problem before we move on, okay? Because if you just hear it like that, you may not realize how hard it is. It is pretty hard. And if you look at this, you're probably glazing over right now, and believe me, I am too, because this is just the first 20 amino acids, the first 20 residues of the protein. And here are the coordinates of all their atoms, what you're looking at. So this is a ton of stuff. This is only the first 20 of those balls. And there's actually a lot more of the balls there. And each of them shows the atom positions, and so this is only a small chunk of what you'd be expected to predict. You have to predict and recover these atom positions in free space, each X, Y, and Z. Now that's very hard. A typical protein has around 2,000 atoms. I didn't put them all in the picture, but they're usually around 2,000 atoms. And it's very hard to find the minimal configuration configuration that minimizes the energy.
Are these coordinates only the carbon backbone coordinates, or
Yes, I only
Just
put,
say all
only
of
put a small number of the
they're not all
yes,
the whole?
that's right.
Whole
Yeah, so this is only a small chunk of what we have to predict. What we really have to
But
predict.
this is only part of that small chunk.
Yeah, right. It's only part of, not only that, it's like a chunk of a chunk. There you go, it's the backbone atoms. And backbone atoms are particular, they're the atoms that are actually plotted there. There are actually a lot more atoms in the actual protein, which I didn't put there. Otherwise, the protein would just look like one giant ball. But there's actually a lot more there. This is only a chunk of
But
a chunk.
on average, how many atoms are there?
About 2,000.
No,
Yeah.
in each amino acid.
Amino acid around 10.
10.
Yeah. And they're usually around 200 amino acids in a protein, which is how I got to the 2,000 number. So, I mean, 10 is the average. There are some that are up to, I
10,
think, 15 or so.
3 dimensions, or is 30
Right.
parameters.
Right, yeah. So actually the number of parameters is larger, although I'm not going to get into this today, but exactly, but there's a smaller, there's a 2,000 dimensional space of that's actually, the dimensionality of this problem is actually only 2,000 dimensional because there are constraints. The bond lengths and the bond angles fix it so that there's only one free parameter per atom. Okay. All right, so now, one other comment about that is when you are moving to the optimum, one of the big challenges is evaluating this energy function. That is by far the most expensive part computationally of the procedure. Why? Well, every time you evaluate it, there are actually n squared computations, one for every pair of atoms in the structure. So with n atoms, there are n squared pairwise distances that you need to evaluate. In fact, I did a winner profile of my code, and I found that just the computation x squared plus y squared plus z squared took up 80% of the runtime. Why? Well, we had to evaluate all these pairwise distances between atoms. So there's a huge number of these that dominate the computation. Okay. Now, so what's the idea in FRES? FRES is due to Sam and some other colleagues, so we have to give him his props for that. The idea behind FRES, FRES tells you how you would go about tweaking this structure until you reach the minimum. Okay? The idea behind FRES is that you take a small piece of the structure. Okay? There you go, a little chunk there called a loop, otherwise known as a fragment. What you then do is regrow it randomly, so that the rest of the structure remains fixed, but that loop piece is regrown. And then what's the big benefit of doing that is saving on the number of computations. Why? Well, if all you do is move the things in that fragment, then there are only k squared, if k is the length of the fragment, there are only k squared plus nk evaluations that you need to do of distances. Because relative to one another, the atoms that are outside the loop stay fixed. You don't need to reevaluate their distances and their energies, just the ones for the fragment that you tweak. So doing this move saves a lot of computational time, and that's the motivation for doing this. It's called FRES, which has this crazy acronym, so FRES is the name. Now I'm going to play a little game. Okay? The game goes like this. Here we have a loop that I just isolated there, and I zoomed in on it. Okay? And here are some possible ways of regrowing it. Okay? In the part here. The opaque balls are the regrowth, and And notice that they're all a little different. Now, what you're looking at here, there are two of them.